Section 6.2 introduces us to a new technique, one in which we learn a way to integrate a function that looks like the product of two pieces. Now, the problem with this technique is that if you take it the wrong way, it's not going to help. And sometimes it's not the right technique for the job. But when everything else fails, this is a good place to look. So let me introduce you a little bit of the background. We'll look at the theorem itself, and then I'll do a couple examples. So if we start from two functions, f of x and g of x, that are differentiable, then we know from Calc 1 how to take the derivative of their product, right? We take f of x multiplied by g of x. The derivative occurs according to the product rule. We would get f prime of x times g of x plus g prime of x times f of x. Fantastic. Now, what would happen if we integrated this on both sides? Well, if we integrate on the left, because of the fundamental theorem of calculus, we just get f of x times g of x. If we integrate on the right, we're going to get the integral of f prime of x g of x dx plus the integral of g prime of x f of x dx. Now, this is a little bit strange because here we have a product of two functions, and here we have two different integrals. But this is supposed to be a technique that lets you integrate just a product. Well, here's how we view it. We're going to take f of x g of x, and we're going to subtract this piece right here, minus the integral of g prime of x f of x dx, and set that equal to the integral of f prime of x g of x dx. And what we're thinking is that in order to solve this product, if one of them is a derivative and the other is not, then this one, to write it over here, stays and we just take its derivative. And this one, we're going to integrate and write it over here. So if we have a function that we know is easy to integrate, multiplied by one that's easy to take the derivative of, then we can use this technique to change how our integral looks into this problem. Even though this one we couldn't do, maybe there's a way in which this one is now doable. So that's the idea behind integration by parts. Typically, the way it's stated is the following. We're saying the integral of u dv, so u plays the role of g, and dv plays the role of f prime. It's the derivative. This will equal to u times v minus the integral of v du. So we're going to take our function, the derivative function, and it's going to look like the same function u, the antiderivative of dv, which is now v, minus, we're going to integrate v, so this antiderivative, multiply it by du. So this is a way to change an integral problem to look something different that is now solvable. So this is really the formula that you have to know, memorize, and mark. Keep this in your mind. The integral of u dv is uv minus the integral of v du. Once you know this, you have it memorized, you can start using it. And let me show you some examples where this works. And I'll give you a warning as to what could go wrong if you don't set things up correctly. So let's get started. So up here, I'm going to put my formula. The integral of u dv equals uv minus the integral of v du. All right, and we're going to do, our very first thing is going to be the integral of x e to the x dx. This is a product. We don't have a formula. We don't necessarily know what function If you take its derivative, it gives you x multiplied by e to the x. And so this seems like a perfect setup for an integration by parts. And the way we set it up is we have to choose which function becomes u and which function becomes dv. Now, in general, u is going to be the one that we take the derivative of because u becomes du over here. So we want to choose a u here that's going to simplify or get rid of one of the parts, one of the pieces. And if we let u be x, then its derivative is just going to be dx. And that's going to make this integral much easier. So we're going to choose that. We're going to let u be x. And so dv is going to be e to the x dx. Notice that I always write everything else as my dv. This means that my u du should completely substitute every piece that we have written here. So u is the x, dv is the e to the x dx. Now my substitution is complete, but I still need to compute the other pieces that I'm going to need. In particular, I'll need to know what du is. Well, it's the derivative, so that's just dx. And then I need to find what v is. V is the antiderivative of this. Well, e to the x is great because it's its own antiderivative. So v is just going to be e to the x in this case. So this partial substitution works beautifully. This is kind of your prototypical example of why integration by parts is great, and it works out fine. So we start by writing that this equals u times v. So my u is x. My v is e to the x minus the integral of v e to the x du dx. And now we went from a problem where we had a product to integrating where we don't have a product. That's what you want. If you get to this stage, you can just integrate and be done. So this becomes x e to the x. Antiderivative of e to the x is itself. And don't forget to add your favorite constant c at the end. And so here we have it. The integral of x e to the x dx is x e to the x minus e to the x plus c. All right, so this one worked super, super well, right? This looked beautiful. But if we had chosen the other way around, right? Suppose we had set it up where instead of u being x, we had chosen that u was e to the x, and then dv would have been x dx. Hear me out, and I'll show you what happens here. Then du, the derivative of u, is e to the x dx, because e to the x is its own derivative. But v becomes antiderivative of x, is x squared over 2. OK, well, it looks like we can just plug this in. So we plug it into our integration by parts formula. We get u e to the x, v, times x squared over 2, minus the integral of v, x squared over 2 du, e to the x dx. And now look what happened. We started with something that had x e to the x, and we ended up with something more complicated because the power on x increased. It became x squared over 2 e to the x. So if you're doing things in such a way that the problem increases, you're going the wrong way. You know you've set up your integration by parts exactly switched. So in that case, you just need to go back, stop, cross it out. Don't erase because it may not be over yet. Try the other direction and see if that helped. Let me give you a bit of a warning on thinking we've made the wrong choice. Let's try one more, and then you'll have to tell me what you think of this. All right. So we're going to let's do the integral of cosine x e to the 2x dx. OK, so this looks potentially interesting. It's a product. We have cosine, we have e to the x, and it looks like we should try to do some kind of integration by parts because we have a problem with the product. But we don't necessarily know which one is better as our u or as our dv. In this case, when you take derivative or antiderivative, both of these you kind of know aren't going to get any simpler. It doesn't look like we're going to make any progress. So I want to show you how you can keep going and still land on your feet. So let's start by letting u be, let's go with e to the 2x dx. I'd rather take derivatives with u because I want the 2 to be in front instead of having 1/2. And then dv is going to be cosine of x. U is just either 2x, dv is cosine of x dx. Right, we want to keep the d's together. OK, so now I've substituted into my u and my v all of the pieces that we see in the original problem. The next step is to finish the 4 pieces. So u, I need du, which will be twice e to the 2x dx. This 2 comes from the chain rule, right? When you take the derivative of e to the 2x, you get itself multiplied by the derivative of 2x, which is 2. For dv, the antiderivative of cosine is sine. So this seems pretty much OK. So we do this, and we plug in u times v. So we're going to get sine of x e to the 2x minus the integral of v du. This will be sine x times 2e to the 2x dx. And now it feels like we made no progress because we went from cosine times e to the 2x, and now we have sine of x e to the 2x. But sometimes you just have to do it more than once. Let me clean this up a little bit more just so that we can see what's going on. This is sine of x e to the 2x minus twice the integral of sine x e to the 2x dx. I don't need a parenthesis here. So the trick here is we're going to do integration by parts on this a second time. And at this point, it's crucial that we keep u as e to the 2x. If we swap the 2, we'll just undo what we did, and we'll get nothing. So we have to keep going in the same direction. We're going to need, once again, to have u be e to the 2x. dv this time is going to be sine of x dx. And so du becomes twice e to the 2x dx. And then v is negative cosine of x. So just this piece, just the piece on the right becomes the integral of sine x e to the 2x dx becomes uv, which will be negative e to the 2x cosine of x. I put the negative in front or else it'll look like a subtraction, but it's a multiplication, minus the integral of v du. And v is going to be negative cosine of x times twice e to the 2x dx. And these negatives are going to cancel, so I'm going to get a plus right here. So this piece I can put right back into there, right? They're the same. So original integral becomes the sine of x e to the 2x minus twice negative e to the 2x cosine of x plus the integral cosine of x, I'll put the twice outside, cosine of x e to the 2x dx. And now it feels like we've completely lost because we end up with this piece is equal, and we still have it here. We've made no progress. It's still the same. But there's a last trick. we're going to call this integral